Hi Rosna, we can start now. Yeah, please.
Hello, everyone. I hope everyone can hear me. So this is Roshna. Before we begin with the webinar, our fourth webinar of TIECONN, I would like to give a quick introduction. So can anybody confirm that my screen is visible and I'm audible?
Yes, we can see your screen.
Yeah. So TIECONN stands for Technical Innovation and Engineering Collaborative Network. So today we'll start with the fourth webinar. So I'd like to give a quick introduction. So TIECONN aims to be a global hub or community of engineers from different cross disciplines to uplift the engineers through the technical empowerment, innovation, and collaboration. To name a few, I would like to give a few activities which we will be performing. So we'll be conducting technical webinars with the expert panels, and then we'll also be conducting training programs and workshops, and there will be career guidance and mentorship programs from TIECONN, and also we'll be sharing engineering knowledge from industry experts. So what is our vision and mission? Our vision is to become a global recognized collaborative engineering platform where innovation, knowledge, and community converge to shape the future of MEP projects and other technical industries. So talking about our mission, we empower young professionals by guiding them, giving them expert knowledge, and also we connect passionate engineers, experts from different platforms, be it consultant, main contractors, MEP contractors, or from facility management or from sites. We also promote sustainable design, smart engineering, and global best practices through collaboration through borders. And TIECONN also aims to recognize exceptional performance of engineers in
Hi Rosna, are you there?
Kumar.
Yeah. Yeah, there was some issue in between. Yeah, okay, fine. Please continue.
Yes, and myself, I'm Roshna Viswanathan. I will be the woman vice chair. And then we have Mahathir Jamal, head of country chairs, Asif Akhtar, secretary, Balaji Raghavendran, vice secretary, and we have country chairs who will be taking care of TIECONN activities in their countries, and they will be leading the TIECONN activities in their respective countries. We have Baharuddin from Bahrain, and we have Mohammad Rashid from Qatar, Mohammad Asar from KSA, Mateen Udain from Pakistan, and Anwar Shahnad from UAE. And country vice chairs, Ilyas Yusuf from KSA, Sugan Namashivam from UAE. We have Nagarajan Chandran from Qatar, Ashfaq Ahmad from India, and Ahad Ullah from Pakistan. And our technical advisory and awards panels will be Altaf Hussain, and we have Mohammad Rizwan Afsat, Blessing Fari, Saeed Amir Basha. And our youth and student division, we have Nabil Baharuddin, youth chair overall, Darren D'Souza, youth co-chair overall, Krishna Prabhu, Mohammad Jabir. So we are yet to conduct an event. So our upcoming events will be organized by Vigneshwaran, Murad Ali, Mohammad Bashir, Mohammad Ashlan Said, Nagarajan K, Arun Murthy, Abhishek Raja, Ellen Chelan, Mohammad Tafiq. And our social media activities and marketing will be handled by Swati Suresh, Christo Pitangachan, and Karthik. So today's topic is chilled water pump head calculation. So why chilled water pump head calculation is important is that chilled water system essentially is a closed loop system. So the system to function properly, not just a chiller with a high efficiency ER, it doesn't mean that the system will function properly. So proper design is mandatory for a system to function properly. So today's topics will be understanding the system requirements, calculating accurate total dynamic head, considering pipe losses, fittings, elevation, and equipment pressure drops, and also optimizing pump selection for energy efficiency. So these topics today, the session leader is Mr. Victor. He's a mechanical manager from RELK Consultant and Engineering Company in UAE. He's having overall of 15 years of experience, and he has successfully delivered over 500 plus projects in design across diverse sectors, as mentioned, like in commercial, residential, industrial, retail, data center, and more, many more. So I wouldn't want to take much of his time. So let's move ahead with the webinar. So I'd request Mr. Victor to share his screen and start the webinar.
Hi everyone. Good evening everyone. Thank you for joining us with the insightful webinar, and special thank to TIECONN for hosting this event. We are thrilled to have such a wonderful group of participants, including engineers, consultants, contractors, and HVAC professionals, all eager to deepen their knowledge. Today's webinar focuses on the critical aspect of the HVAC system design, chilled water pump and calculation. Whether we are working as a consultant engineer, a contractor, or a system designer, understanding pump gate calculation is essential for efficient and cost-effective chill water system. A well-calculated pump head optimizes system performance, reduces the energy consumption, and prevent operational issues. In this session, we will dive into the fundamental of pump head calculation, covering key concepts such as total dynamic head, friction losses, and pressure drop. We will explore the practical method, including the Rosen-Williams equation and equivalent pipe length techniques, and discuss how to account for the system component like pipes, fittings, walls, and coils. By the end, you will have a clear step-by-step approach to performing accurate pump head calculation for real-world applications. Let's get started this the essential topic. Okay, can you move on next slide? Okay, so first one, what is a pump head? The pump head is often referred as a dynamic head in the context of chilled water system. Is the total energy that the pump must be imparted to the fluid to overcome all resistance and move it through the system. It is measure of the pressure or energy required to deliver water from the pump to the farthest point in the system, accounting for the elevation, friction, and other losses. In HVAC application like chilled water system, the pump head is critical for ensuring the chilled waters circulate effectively through the cooling system, including the pipe, coils, and fittings. Okay, next slide. Here you can see this diagram. Usually, the chilled water system is a closed loop system. Let's take a look at the diagram. This is detailed schematic of the chilled water closed loop system. The key components involved in the circle in the loop systems. You can see there's a chiller, and you have the pump, and you have this air separator, and then you have the pressurization unit, and the longest path of the air was there, and pipe fittings and walls and everything is there. Understanding the layout and the function of each component is crucial for calculating the pump head. Each components contribute the total resistance. The pump must be overcome that one. Let's break down this system to see how these components interact the typical HVAC setup. First one is a chiller. Chiller, you already know everyone. The chiller is heat heart of this system, responsible for cooling the water by removing the heat through the refrigerant cycles. Then the important component is a pump. The pump is circulating the chilled water through the system, overcome the all resistance. And then you see the pressurization unit. The pressurization unit is accommodate the changes in the water volume due to the temperature fluctuation, maintain the system pressure and preventing the damage from the essential. The thermal expansion, it is also helped to remove this air from the system. Air separator, then the next one is air separator. The air separator remove the air from the chill water, preventing the airlock and improve the system efficiency. And the next one is goes the air handling unit. The air handling unit or the heat exchanger that use the chill water to cool the air, which is then distribute the building. Okay, that's the diagram. Can you move on next slide? And you have Raghavan, can you move on next slide? Yes. The previous one. Now go on the previous one. Slide 3. Can you move up? Yeah, that's okay. Here let's break down the components of the total. No, the next one. Yeah, this one. Keep it this. Let's break down the components of the total dynamic head or TDH. The total dynamic head in the chill water closed loop system is sum of the all energy losses the pump must overcome to deliver the required flow rate. The slide outlined key components. One is static head, the second one is friction losses, and third one is equipment pressure drops. Okay, so I will explain one by one. The static head, you already know this one. Static head is the energy required to lift the water to the higher elevation, representing the vertical height difference between the pump and the highest point in the system. It is measured by the feet or meter of the water depend on the gravities. Okay, in a first important thing is in a closed loop system, like one shown in the figures, the chill water circulate continuously in the shield loop. So water leaves the pump and flow to the chiller and AHU, other components, and return to the pump the same direction. Because in a pressurized systems, the static rate is actually zero because it's already pressurized. So when the line is pressurized, it's a closed loop system. So a closed loop system, the lifting pressure is balanced by the return of the chill water flow. So in this scenario, so no need to consider for the static rate for the chill water pump get calculation because the water is already pressurized in the system. And then the friction losses. The friction losses refer to the pressure drop that occur as a water flow to the pipe, fittings, and walls, the chill water system due to the resistance caused by the internal surface of the components. These losses of pressure must be overcome by the pump. So it is critical part of the heat head calculation. Third one is the equivalent pressure drop, the equipment pressure drop. Equipment pressure drop is refer to the pressure drop that occur as the water flow to the various components in the chill water system, such as chiller, heat exchanger, cooling coil, and then the control valves. Each piece of the equipment impact the flow of some extent, and the pump must be provided enough cut to overcome the losses. Surely these losses, we'll get the data from the manufacturer data sheet. Surely they will provide based on our flow rate. They will provide the value of the pressure losses. Next slide. Rahul, can you move on next slide? Yes. Okay. Actually, before starting the pump head calculation, we have to gather all the essential data, including the pipe length, what is the diameter of the pipe, of what kind of material we are going to use. Usually we will use black steel, and then the carbon steel also we'll use. When it is come from the underground, we will use a HDP pipe. Then determine the flow rate based on the cooling load calculation, and then identify the pressure drop of all the equipments along the longest path, and finally calculate the equivalent pipeline for the fittings and walls losses using ASTRE standard or the manufacturer data sheet. Before proceeding the hydraulic calculation process, you have to understand these are all parameters in the pipe, what kind of pipe and material and everything, and then the equipment losses and friction loss, and then the fittings losses and everything. And finally, you have to make the margin safety factor 10 to 15% you have to consider for safer side. Here is one calculation is there. Example, can you move on the next slide? I will explain step by step. Yeah. So the first one, because our calculation going to be based on this Williams equation. So Williams equation, the most of people are already aware of this one. The HF, which means the friction head, is equal to 10.674 into L into N. L means length of the pipe, and then Q is the flow rate. Q 1.852 divided by C over 8, 1.852 into D is diameter over rate of 4.87. This is SI unit. The empirical unit you have 4.7. Similar. All other thing is a similar one. For only this, the constant value will be changed. And then in this calculation, the friction loss, the unit is in the metric, sorry, the SI unit, so it's a meter. And then the length is meter. The flow is meter cube per second. And then C is a roughness factor. It will vary based on the pipe material. If we are using the carbon steel pipe or the black steel pipe, it is around 130. And if you go for HDP pipe, it will come, I think, 150. So it will come. Then diameter, of course, it will come the meter. One example is there, 200 meter length of the pipe, and the pipe diameter is 50 mm. And flow rate is 0.01 meter cube per second, and the pipe is I consider here the carbon steel pipe. So the the roughness factor is 130. So we put this all data together, we will get 111.26 meter will come. And then move on next slide. So usually you have to do this based on this from one by one. If the state it is already described the bottom slide. So each and every pipeline you have to do this one. Similar like a fitting also you have to do this one. And then remaining the equipment's pressure drop, you will get it from the manufacturer data sheet. Okay, move on next slide. Okay, then you can see this here. I added the the walls and fittings data sheet. This is manufacturer data sheet. Calculate the equal pipeline for fittings and wall using the ASTRE guidelines or manufacturer. Echo. Can you name someone? I don't know.
Yeah, we feel the echo.
What about now? Is it okay?
No, again echo. Echo is there.
Can you mute? What about now? Is it okay? It is still is echoing.
No, still echo is there. No, can you try again? Yeah, can you
Can
unmute
you
and
try
play again?
again? Yeah, can you unmute and play again? I think my side is okay. My side is okay. Nagaraja, can you check from your side?
Anybody else has the same issue? Are you feeling like echo or is okay? Can anyone unmute and from?
Now it's okay, right?
Now it's okay.
Yeah, it's
Yeah,
fine.
now it's okay, right?
Yeah, it's fine. Yeah, now it's okay. Yeah.
Okay, so calculating, okay, the next slide, okay, pipe and walls, the fits for fitting and walls. Calculate the equivalent pipe length for the fittings and wall losses using asterisk guideline or manufacturer data set. So you can get it from here, the all data is there. You can see this a walls and everything is there, and corresponding the pipe sizes, the left side, you can see this one. Based on that, you can get the equivalent length. Then once you get this value, you can put it in the William equivalence equation, and you will get this pressure drop of each and the pipe and fittings, sorry, the walls and fitting losses. Can you move on next slide? Yeah, here is, see this, the someone is raised, okay, no problem. Okay, here you can see this.
Question we can discuss
Yeah.
in the end of the section because someone is
End of-
asking how to find out the flow rate. Mr. Danis, we can discuss this one in the later end of the stage. Yeah. Thank you.
Okay. Okay, and you can see this, the fitting losses. Okay, see is each and every fitting is there. The bend L or 45 degree or 50, 90 degree. So all type of fittings and everything is there, and corresponding pipe size also there. Okay, can you move on next slide? Can you move on next slide? Okay, yes. So you can see this equipment pressure losses. Usually equipment pressure losses, we will get it from the manufacturer data sheet. According to the manufacturer data, you can obtain the pressure drop values for all components. This value should be added the overall pressure drop calculation. For example, I have some values there. You can see this one, the value. Cooling example before, yeah. Cooling oil, the range I mentioned is a sample value, but it's not accurate one. 3 to 4.5 meter, and chiller 1.5 to 3 meter. And control walls, the control wall like a PIC wall, other motorized control wall, 0.6 to 1.5, but it's not a fixed value. The value will change based on your flow rate. And then once you can add all the values. Any more? Next slide. Okay, then the final one. So once you calculate all the losses, the pipe losses, fitting losses, walls losses, equipment losses, then you have to add it everything together. So to combine all the pressure losses, including the pipe friction losses, fitting losses, wall losses, equipment pressure losses, and then add the safety margin. That is a very important one to obtain the final chill water pump value. So there is based on above the data here, they mention yes how much each and every the losses. The static head, the closed loop system static head is 0, so that's why I mentioned 0. And friction losses, sorry, the friction head based on the pipe losses 1.4 meter, and then fittings and wall losses 1.8, so total is coming 3.2. And then equipment losses 8.5 meter is based on above the slide. And if you add it all together, so 11.7 is coming, and then safety margin. So total value is coming 13.45. So it's round up 15 meters meter actually. Can you move on next slide? Okay. So once you got this the value, then you have to select the pump. The major thing is the pump, the chill water pump. This slide you can see this the curve, the pump curve is based on the flow rate and the head. So once you got this value, you have to select the here in the the pump curve. That is also very important. So you'll get here from here, you'll get the efficiency curve also. And move on next slide. Yeah. So here you can see the final one, sample schematic diagram is there. So here I mention each and every node. When you do the calculation, if you go for detailed calculation, you have to you have to make similar way, because each and every node wise you have to mention. Example, here I mention, can you zoom in a little bit? Raghavan, can you zoom in? Actually, I started from the pump side, from the discharge side. I put the node and node number 1, and then next it is when it reach the bottom of the riser side, the node number 2, and then it is distributed along the path. This is the longest path. So if you have a high-rise building, you can provide similar basis. Yes, yes, zoom it. Okay, no problem. You keep it. See this one? Clearly is there. The node number 1, starting from the pump side. The pump side start from this. You no need to miss any any fittings or any item actually. This is if you in the pump side you have the flexible connection. Will start from the flexible connection, and then need to distribute based on that one. And then the pump side you have this all type of you have the wall arrangement will be there. And then the node number second you can see this start from the riser bottom, and then you have the first floor, the branch line is there. Then after the pipe size will be changed, because the pipe size will be changed on the flow rate, right? So once the pipe size change, then you have to change the more node number also. Then you can see the second floor. The second floor, the node number I put 4, node number 4. Can you zoom out? Can you zoom out? Yeah. Can you zoom out? Yes. Then here I only I considered 3 floor only. So you have to do based on this scenario. If you have multiple floors, you can do based on that. This is only schematic diagram. So when you go for the shop drawing, you have to provide like isometric diagram. So you have to calculate. If you want accurate calculation, you have to make your own isometric diagram. So in the isometric diagram, you have this up and down, and then everything clearly you can mention. You can mention easily, clearly, and then you can easily understand from that perspective. You can get each and every value accurately. But here I only draw the schematic diagram. Schematic diagram, sometimes the up and down, you cannot be able to mention clearly. So when you do this proper calculation, during the shop drawing stages, you have to make the isometric diagram. So the isometric diagram, so the each and every up and down, that is a very important, because when you do the calculation, you can see here you get everything is there. Pipe, the components and the fittings and everything is there. But when you do this isometric diagram, there you can easily find out the each and every small drop, and then the rise and everything you can do that one. And based on that, can you go next slide? Can you go next slide? Yeah. See here, this is on Excel calculation. Okay, I made it based on this above calculation. So when you start from this pump side, the pump, what is there? The flexible connection. You have to add the flexible connection, and then the straight pipe, and then whatever the wall gate was, and then the PAC wall, whatever the strainer, whatever it is there, you have to add one by one based on the node number. Here I did not mention node number, but you have to mention when you do the shop drawing, you have to mention. This is only for detailed calculation, but detailed calculation no need to mention, because usually detailed calculation will not be present, to anyone, because the consultant said we will do only like such a kind of calculation. But when you do from the contractor side, you have to submit the calculation to consultant engineer. So you have to mention each and every one node wise. then only they can easily understand what are the commons, or what are the things you consider, where did you mention anything or not. Like that, you can easily find out from that perspective. But here it's not necessary, because we will do usually for our side only based on the detailed design drawing, not like a shop drawing. So shop drawing only you will get up and down based on this coordination. But here we will not do that much accurate coordination. Just overall coordination we will do this one. That's the reason I did not put here the node wise. But when you do the shop drawing, you would put each and every node wise. Each and every node wise, you have to mention everything clearly. But here is mentioned state by state. Usually, if you see the above slide, I mentioned is what is the total pipeline, and then flow rate, and then what kind of material. Here is like the black steel iron, so it's for black steel pipe. So, and then finally you can see this in the friction losses. This is friction losses table. I put the Hazen-Williams equation, so it will automatically appear the value, and we'll see the total summarized value is down here down. You can see this, the total sum. Can you zoom in down? Raghavan, can you zoom it down? Yeah, it up, down. Yeah, you can see this one. Here I consider 10% margin. This is the total. Can you see? Can you zoom in the volume? The value area. Value area. Can you go to the value area? Total. Yeah. See here. This is a total value based on this above diagram. 7.38. Sorry, 363. After adding this safety factor, got almost 8.1. So this is the pressure drop. I think if you want the detailed more, then we have to go for another one webinar. There I will take any one sample and then I will explain node wise. So due to the timeline, I cannot go for that much detail here. So that's it for today's webinar. If you have any question, can you put in the chat box?
Yeah,
If
when it
anyone
comes
has,
to
yes.
when it comes to pump head calculation, it is for everywhere. Everyone his mind is there that like if you are going with any closed loop, as you mentioned that there is no need to consider the static head. So the pump is pumping the water from ground to top level. Again, the water is coming back as a closed loop. So I believe that everyone has this in mind. So closed loop, there is no need to consider the static head. So can you explain? I think that is what everyone thinks, I think. Yeah. So this is the same
Okay.
strategy we need to follow for because the plumbing system also we have the circulation pumps for the hot water. So there also we have the circulation pumps. So it's common for all. Yeah.
Okay. Okay. So when it is go for the why I did not consider static at here? The stat, this usually when you go to the one close to system. But here we are doing the calculation of the pump gate because the system is already pressurized. We are doing the pressurized system calculation, not like the the chill water system calculation. When you do this pump gate calculation, it's considered like a pressurized system. It's a pressurized system. So why we are not considered in the what you call the static head here? I will explain a little more on that one. Okay, so usually why I neglect in this closed loop systems. In a closed loop system, the water start and end at the same elevation. So pump for every upward pipe run, there is a corresponding downward run. The water return to the pump. So elevation gain losses, it's cancelled from this. Because of this one, there is no need to consider this the static head. The closed loop is a filled. I already explained this. Closed loop is a filled and pressurized. Means the pump doesn't need to lift the water against the gravity to fill this system because it's already filled. The pump's role only overcome the friction and the losses, not to lift the water the highest elevation. Most HVAC loops, the loop design, the common like a chiller, pump, and AHR plays a similar elevations. Even if there is minor elevation difference in the closed loop system, you have to neglect that one. So this is there is exemption also is there. If the system has a significant elevation difference, which means supply line and the return line, there is a significant difference is there. So that time you have to consider static. How much difference is there? The return line is not like the balance to the supply line. That time how much difference is there? So then you have to consider small amount of, based on this difference, you have to come and consider the static gate, because it will have to overcome. Some of the building, there is due to the structure, due to the building structure, this will come. There is up and down based on this one, it will come. So that area I have to consider. But this is very, very rarely will happen. So most of the case is commonly we don't need to consider for the static gauge. And another one, if the expansion tank or the air separator is placed at much higher elevation and the system isn't fully pressurized, there would be a small static pressure that you have to consider. There also you have to consider small head, because it's the location of expansion tank and air separator is not in the same location of the pump. It's located at somewhere. If it is located somewhere due to the space concern, that time also you have to consider small static gate. Most practical solution, we will not consider any static gate. Okay.
Yeah,
Hi,
so
sir. I have one
yeah,
question also.
yes, so
Yes.
Dan is, sorry, who is this?
I am Mohammed Bashir.
Yeah, please ask.
Yes.
Fine. Yeah.
Yes, go ahead.
For the head now we calculated. For the flow we are getting from the individual multiple units, indoor units, we are taking the flow of the total pump for the pump, right?
Yes. Yes, the flow, this one how to calculate. The flow is based on this, the heat load calculation. So based on that, you will get the flow rate. So once you get the flow rate, you have to make one the diagram, which means like a schematic diagram. So easily do this calculation, or else flow diagram, the flow plan also is okay. But use the schematic diagram is you can easily place the fittings. The fittings, which means mainly the fitting is a concern, because some people is they miss the fittings. That also it will impact the overall system efficiency. Sometimes it will not will not get the proper cooling due to this issue. The most time the shop drawing stage, the people will ignore these values, which mean the main fittings were like a bend and the ready to T and whatever it is, they will ignore it because they will not consider due to this the timing line. This be some of the contractor, what they will do, they will take the IFC drawing and then put it in their title back, and then they will do the like a similar node number, and then they will present their what you call this, the head loss calculation. But this one, the real issue is in the coordination time. So coordination time, there is up and down will come. So that is a very important. That time, what will happen? The last, the furthest point, you will not get enough cooling. So the people might think that during the commissioning time, it is not related to chill water. They will think the issue of the coil or some other issues. But the issue is because of this one. Because if we not consider proper the fittings, why I'm repeatedly saying the fitting is main important, because you will definitely will consider all the valves and then the other commons, because the major one part is the major one. But mainly the people will missing the fittings. Okay, so if we miss any fittings, it will definitely affect this efficiency of the chill water system. Okay. And one more question.
Yeah, that is also the same point. How to? I think Mr. Dan is he has asked the question that how to find out the flow rate for this system. So that one you answered now, that from the cooling load calculation we will find out the load.
Excuse me.
Yeah. Yes.
Yes.
I am asking the flow rate for the friction losses. For example, we will know the flow rate of the entire system, but when there is a reduction at point number 3 and the dia is reduced to DN80, at DN80, what should be the flow rate? how to calculate the flow rate at that
That is,
particular after.
yeah, this is what I said. That one is a Hessen-William equation. There is equation is there. In this equation, you have to put this value. Example, you have the fittings. Okay, example, this fitting is you are asking pipe size or the pipes or fittings.
I'm asking what should be the Q value to calculate the friction.
No, the Q value is based. This is the flow rate, right? The flow rate, if it's from one point to
What should
another
be the
point, is
flow rate?
varying means. Okay, if it is
No, but
varying from one point to another point, this in between the point, you have the flow rate is there. Example, if the flow rate is 10 liter per second, the point 1, the
but
2
how
to
do you
3.
define the flow rate? How can we
This is
say
what
the
I
flow
said.
rate is 10?
The flow rate. This is what I said. Go to the. Can you go the schematic diagram? Can you go the schematic diagram? Rajan, can you? Sorry, Raghavan, can you go the schematic diagram? The last one, the node number schematic. Yeah. See this example. Can you go this chiller side? Okay. See here it's 10.5 liter per second. This is the overall flow rate.
Okay.
When you go for this ground floor, see there is a value is there. The ground floor branch pipe, there is a value is there. 4 liter per
Yes.
second. So when you minus 4 liter per say, so 4 liter to minus 10.5, you get around 6.5. Sorry, not around 6.5 you will get. So node number 3 to 4 is 6.5 liter per second. That is a value. So if you calculate the node number 3 to 4, the pipe size obviously to come for 80 dia, and then the flow rate is 6.5 liter per second. So this
Okay.
you
So
can put this value in
basically,
that. Yes.
also
Yes.
basically we calculate the flow rate for a particular floor and add up all the flows, and then we find the
Yes.
total flow rate.
Yeah,
Yes.
yeah, correct. Yeah.
Okay.
Yes.
And in firefighting system, basically this is not the topic of firefighting, but in firefighting system, every sprinkler has a different flow fighting, so we have to calculate the flow rate of every sprinkler and add up to the main branch header.
No, this one firefighting is a different topic. It's, usually firefighting, you have the coverage areas there. Based on the
Okay.
coverage areas, for example, you have the
Hydraulic area.
ordinary occupancy.
Yeah.
Yes, the hydraulic the area is the coverage area. Based on the hydraulic the coverage area, how to calculate? Because you need to take a example. If ordinary hazard group 1, the coverage area is 1,500 square feet. So how many
Yes.
sprinkler will come the 1,500 square feet? And so around 12 to 13 sprinkler will come. If it is ordinary
Okay.
hazard means. So 12.1
Yes.
K factor. So sorry, 12, K
Okay.
factor is
So
5.6.
basically,
The one
each
sprinkler coverage is 12. Yes.
okay, each sprinkler LPM we find out the
Yes.
LPM or LPS, and then we add up to the
The
branch.
value is only for this coverage of that area, not the entire sprinkler
Yes. Yes.
flow rate. Only the coverage
Yes.
area. So imagine
Okay.
you have this 1,000 sprinkler. Each sprinkler have this value. Okay. Example 13 liter per second. Sorry, 13 GPM. Consider 13 GPM is there.
Yes.
If you add up everything, how much big pump will come? So that's the reason the fire will not happen everywhere, right? Fire will start from one
Yes.
location.
Yes.
So
One
we
location.
are focusing on that location, right? So that is the
Okay.
coverage area. Normal pump.
Okay.
So
So
usually when you do
in
this pump
that
set calculation for
situation,
yes, yes.
in that situation, we should consider what GPM for friction losses. The
What
particular
GPM?
area, yeah, the for friction losses, we should consider what Q, what flow, the area's flow, entire area's flow, right?
No, this is what I said. There is a coverage area is there. Okay, hydraulic calculation. If you go the fire highlight software, there is the chart will come, right? So sorry, the one by one come. When you go for this one input data, there is I think last one you will find the coverage area, and then each sprinkler coverage area, and the flow rate. It will not show the flow rate. Flow rate is automatically based on the coverage area and place a hazard classification. Sorry, hazard classification. You will get the each sprinkler flow rate in this given floor in the coverage area. Example, the 5,500 square meter. There is a 12 sprinkler coming. So
Yes.
it's automatically calculate based on that one. You will get example 300 GPM. That is the flow rate.
Okay.
But if you do
Okay.
manually, there is a manual calculation is there. So each sprinkler you have to calculate and add up 12 sprinkler, you'll get total flow rate. But this is only
Okay,
for flow
thank
rate.
you.
But when you do the head
Yes.
calculation, you need to go for again furthest point. Okay, longest path.
Okay,
So
okay.
usually we'll
Sir, how
calculate
we
based
can
on that one
calculate the
scenario.
Thank
Sir,
you.
This
how we can
topic is
calculate
moved
the
somewhere else.
pipe size?
Sorry, again.
Yes.
Can
Hello,
you
sir.
please repeat? Yeah.
Yes. May I know?
Hello, sir. How we
Yes.
can calculate the pipe size as per the flow
Yes.
in
So the
in
pipe size,
chilled
usually
water
you know the
system?
velocity, how the velocity is there. Usually we go for 1.5 meter per second velocity. And then based on that, you can calculate this flow rate. So maximum you have to consider 1.5 meter per second velocity. Okay. So you have the pipes. If it is very difficult for you to do this, because if you do this each and every, flow rate is very difficult. Do this, sorry, each and every pipe size. Sorry, you need to, if you do the calculation, manual calculation, it's very difficult. It will take too much time. So that's the reason we have the flow chart. The chart is there. There is a range is there. Example, if you have this 2-inch, there is the 2-inch mean you have this 20 GPM to 30 GPM, something like this. You return the flow chart. So you can easily take that one. Or if you have very difficult that one, then you need to do this one by one calculation, one by one pipe size calculation, manual calculation. So it will take longer, much more times compared than
Okay,
this
sir.
flow chart.
And one,
Okay.
uh,
But the
okay,
very important one, the
okay,
velocity you have to 1.5 meter per second velocity.
okay.
Okay.
And one more thing, sir. For the
Yes.
heat load calculation, we are not calculating the flow, sir. We are calculating the cooling load, right?
Yes. The cooling load, the heat load calculation, you will get the chill water flow rate, right? The flow rate you'll get it flow rate. You'll get the air
We
flow rate,
can calculate
and then all
the
the
flow rate
remaining parameter
also.
will get. Yes.
We can calculate the chilled water flow also in cooling app software.
Yes. Yes. Yes.
No,
You will
actually
get. You
he's
get.
asking the no, but actually he's asking the water flow rate. Water flow rate based on the
Water,
delta T we can find out. This we have the formula, no? GPM is equal to ton of
No,
refrigeration into delta T.
if you
That
do
one he's
this
asking.
manual no, listen. If you do this manual calculation, it's no problem. You can do this when you have this each and everything. Each software is not like automatically doing. There is a formula is there. Each and every output you have the formula is there. It will work based on the formula. It's not like you're doing automatically. It will work based on this formula. So if you want to do it manually, you can do this. There's no problem. But it will take times. There is So that's the reason I said if you do the calculation, which will have calculation, you will automatically get this flow rate also, water flow rate.
okay.
So if
Actually,
you do
what
manually, yes, tell me.
actually, sir, we are doing now my current project. We are giving the cooling load and the supplier giving the floor selection. Then that time they are giving the flow rate also for the chilled water. That flow
Mhm.
rate we are considering chilled water for the pump flow and head.
Okay. No, usually when
So
there is a scenario is there, okay? When you do the design, okay, you will do based on the app calculation or it use any other software, or even if you do the manual also, there is a value will carry, right? So when you do the selection, you will not get the same value as per your design. So the value will be changed, maybe 5% or 10%. That's the reason I told you, you need to consider safety margin. Otherwise, you will not, the pump will not enough to, because sometimes there is a building is there is a restricted flow only there. For example, the district cooling system, each and every building they already allocate the flow rate. Each and every plot they already allocate the flow rate, in water flow rate, how much is required. So you have to adapt within this flow rate. So sometimes maybe it will, if it is go for beyond your the allocated limit, you have to go for diversity factor. So when you when you add up all this flow rate based on the selection, you will get one final value. I'm pretty sure it will not match your design value. It will some percentage different will be there. So if you are doing this chiller, which means they're not district cooling, then it's fine. You will change the flow rate of the chiller and the pump. Okay.
okay,
So finally, only you
okay,
have to do the selection, not like at the beginning. If you don't go for the beginning, the selection. Okay. So that's the reason
okay,
each and every time the consultant will say, when you do this, the pump selection, when you do the pump selection, you have to submit this pump head calculation. Okay, based on this selection of each and every individual unit.
Okay.
Ready? Yes.
Yeah. Hello, sir.
Yes.
Hello. For
Yes, tell me.
district cooling and standard chiller, the delta T is both are same, or the delta T
No.
is
It's a different,
different for
different because that is a water
what
cooled
is
chiller.
it?
There is a,
Yeah.
usually when you do this your own chiller, you will go for why you are going to air cooled chiller, because when you do the water cooled chilling, you need a cooling tower. That is, it will accommodate too much area. So you'll not. There is no issue in the way you have to get this much of area. That's the reason we're going for water cooled chiller, and the air cooled chiller and water cooled chiller. The price is also a little high. So when you go for your own chiller, is usually everybody will prefer for what you call this air cooled chiller. But if you have such a large project, a very big project, then you can go, if you have the space also, you can go for water cooled chiller, no problem. If you have budget also, you can go for water cooled chiller. But if you have a small building and like a building type based on the type, high rise building, low rise, it doesn't matter. But if you don't have this that much budget plus the space, you usually directly need to go for air cooled chiller. So air cooled chiller, there is a temperature is different. The delta T is different. And water cooled chiller is delta is different. Okay.
Okay.
Example, water cooled chiller, you will get 1.5 GPM per ton. Okay. But when it is come for air cooled chiller, 2.6 GPM per ton. It's around value. It will little bit up and down will come, but this is the default, like a default value. Okay.
Okay.
Or if you want to do this manual calculation, you have the manual calculation already. That GPM is equal to 24 into delta T, and so you will get it that one. You'll get the tonnage based on that one. That is a manual calculation. Usually, manual calculation will not do this one because one by one, if you do this, it will take too much time. So we will directly go for software. Okay. Or like a similar what I did, the one Excel sheet, you will put this value, you will automatically get all the output. Any other question?
Hello, sir.
Yes.
The chart you showed here for equivalent length for bulbs, could you please
Yes.
share that? Here you can see that flexible connection is missing. So how much equivalent length should be considered for flexible connection?
The flexible connection is very minimum, actually, very minimum. It's not like a other fitting. So here you will not find it, but we have this as say there is a chart is there, flexible connection also. If it is not, there is a default value is a 0.3 to 0.5 meter you
Meter.
can consider. That's the maximum value.
Okay.
Okay.
Sir, I have one more questions.
Yes.
The schematic diagram, we can see that there are one pump, but in some cases we use two pumps, primary and secondary pumps.
Yes.
Primary, secondary chill water system.
Yes.
So in this case, I have noticed that someone is considering the critical path in different ways. As for secondary pump, they are considering critical path, secondary pump to equipment. I mean load, HU or FCU, or someone is considering secondary pump to primary pump suction. So which one is correct, or what is the differences? Can you please explain?
So when you have this primary and secondary, so both you have to do this because I want to select both pump, right? So example, if the primary side is going to the supply and the return is coming back to the line, this with the return, which means the primary pump. The primary pump mainly focus on the return line. If you have any, return line, sometimes you cannot able to the manage with the primary pump, sorry, secondary pump. That time this primary pump will be undertake this to the consider this pressure loss. So
I mean from
so you
load
mean the
to
entire
primary
system,
pump section.
yes,
Okay.
yeah. So the entire return line to the longest part, the return line to chiller up to the chiller, including the primary pump. The primary to how to calculate the longest path, the return line to up to the pump. Additionally, the chiller line because it will go to the chiller line again, right? Similar, the secondary pump starting from the chiller to the supply end, in the supply side of the longest path. So you'll get this both like this.
Okay, sir, got it.
Okay,
And
because you have to calculate separately both. Or if you
yes,
calculate both, because the routing is like this, right? So in between you have the bypass line is there. That is separate in a separate case. Based on the flow rate, it will open and close. Okay.
okay.
Because the
Uh,
loop is like this only. The loop is between the chiller and the secondary pump. You have the primary pump is there. Between that, you have the primary pump is
okay, so sir, for secondary pump, I have to
there.
consider from chiller to load, and for primary pump,
Yes.
load to chiller.
But always you need to consider loop, huh? Okay. Because it's the loop system, right?
Yes.
Otherwise, you have to provide static. Okay, because we are calculating only the pressure. I'm repeatedly saying we are doing the calculation of pressurized system, not like a empty one. Okay, the pump is always we are doing calculation. Pump get calculation. It means the line is already pressurized. Okay.
Then the sir, chiller loads where it will be added in primary system
Yes,
or
the
secondary.
chiller route based on the manufacturer. For example, you have the 10 liter per second. Okay, the chiller capacity 10 liter per second. So if you go to the manufacturer, they will give this selection data. In the selection data, the pressure loss will be there, the water pressure loss. Some kind maybe it will around 5 to 10 meter head will get. Based on the
But where,
capacity, it will vary.
in which system we will add this, in primary system or secondary systems?
No, you have to add both sides because it's the loop,
Both.
right?
Oh,
Yes.
yes, okay, so I got it. And you are told about bypass line, how
No, the
to.
bypass line only for this, the example, there is a system is there. Okay, constant and variable pump is there, right or not? You need to
Yes.
know this difference between constant and variable pump. So why you are using secondary variable, primary constant, or why you are using both are variable. So you need to know this difference between this one. Then only you will understand why I'm considering why I'm considering entire loop, or I'm considering only partial loop. Okay, because the secondary pump is a supply side. Okay, supply side and along with the return line. That's a line. That's why I'm repeatedly saying this. The bypass line will come, but the suction side is there, right? The pump need to suck the water from where? From the chiller side, right? There is a suction side, right? The
Yes, sir.
secondary pump. So we have to consider that one also, right? Right or not?
Okay. Yes, sir, right. And expansion tank and air vent should be installed before section of primary pumps. So we have to consider the losses of expansion tank and air vent also.
Yes. The pressurization unit mainly you have to consider air separator and the chemical feeding, the dosing system. Air separator is very minimum line because it's coming based on the line where we are locating all the components. Where usually we locate near the pump side. Okay, we will not locate some other area near the pump side because otherwise we have to consider the static. If when you have to consider minimum static pressure. That's the reason we are always keeping these all equipments near the pump side. So the minimum load you have to consider for the what do you call the pressurization unit minimum load.
Yes, sir. And
Okay, the
one more
minimum
question.
losses. Yes.
One more question is that we calculate pipe size from chart or pipe sizer software. Here we put GPM and match velocities. So
Okay.
in bypass line, GPM is not fixed. It depends and
Yes.
varies. So how much
Okay.
GPM should we consider, and how to size this bypass line pipe size?
So maximum, what is the flow rate? Maximum flow rate you have to consider. Okay, so maximum flow rate because the pipe is designed based on the maximum flow rate, not like on the partially or like a 30%, 40%, not like this. The pipe is example if your main pipe is 200 diameter means the pipe line also 200. So which means you have to consider entire flow rate.
Okay, sir, got it. Thank you.
Any more question? We will make one more session like in the detail. Like the last two slides you will see this one the schematic diagram, but it's a very smaller one. That's the reason I didn't explain too much. So we'll go on high-rise building, and I will mention the how to provide the headcloth calculation based on the shop drawing, not like design drawing. Here I present only the shop design drawing. So we will do one more session for that one based on the shop drawing. So we'll get better understanding that one.
Sir,
Because it will take
you
time.
mentioned
That is take time. It will take take 1.5 hour like this, because I have to explain each and every node wise. It would take now too much time.
Sir, you mentioned that for closed loop, static head is 0 because
Yes.
the full entire system is pressurized.
Yes.
So for open loop, there should be static head. So
Yes.
what
You have to
or what is the static head and the cooling tower height?
Yes. Okay. There is one important question you're asking. Example, in the closed loop system, there is a reservoir will be there. There is a cooling tower will be there. Okay. In the
Yes,
water,
open loop.
I'm saying the water cool chiller. There is a what we have. If you have the water cool chiller, air cool chiller, there is nothing is there. But when it is come for water cool chiller, you will have the reservoir and you will have this the cooling tower will be there. So then you have to consider static head. How much the distance from this the furthest point to the cooling tower, because that is only going right. So that one you have to consider, because you have to lift each and every time that line. So there is that height you have to consider. For example, if you have the 5 meter height, means you have to consider that 5 meter in the static head. It is not 0. You have to consider 5 meter static head.
5 meter is static
But
head. Is it
Yeah.
as per
If it
thumbs
is,
or?
yeah, if it is in the water cool chiller. So water cool chiller means you have this reservoir will be there, you have this cooling tower will be there. So that time you have to consider this minimum static height based on this the distance from this cooling tower to the system. Yes.
Cooling
But sir,
tower to the
that is
system.
for
I mean,
condenser pumping.
Yes.
sir, cooling tower to the system means cooling tower to chiller height distance.
No, you don't want to consider that distance. Only the minimum, which means that where you are locating that one. That is a minimum. Example, I'm locating the ground side. Okay, ground side.
Okay,
You will not put you will not place in the ground. I mean, under the ground side. You will have the elevation is there. You will put it in the one platform, right? Because it's the gravity is working like the gravity line. So have to that height you have to consider. Ground floor to how much distance you have put in the cooling tower. That you have to consider. But when you place in the roof side, so your water is already reach up to the roof. From there to cooling tower, how much height is there? That you have to consider. That's what I said. Minimum height will come. Minimum static height you have to
Actually, we
consider.
have a written pipe as well, right?
Yeah.
So we need to look at the difference in the vertical height
Yes.
of both supply and return. That difference to
Yes.
be considered,
Yes.
not
Yes. Exactly.
entire line.
Exactly. That you have to consider.
Yeah, because there is also a parallelly supply as well as return.
Yes. You
So
have both.
yeah,
Both we have this.
yeah. So only
Because
the
that
difference
return
of the
is coming
vertical
to the
height to be
system.
considered. Yeah,
Yes.
only the difference between the vertical height of supply and return to be considered.
Exactly. That's the one you have to consider. Yes. Any more
Sir, in
questions?
fire,
Yes.
fire pump hydraulic calculation, we consider static head, dynamic head, and residual pressure head.
Yes.
So for open loop, should we consider residual?
Yes, the open loop system is entirely different. When you come for open loop system, you have to consider everything. You have the residual pressure, you have static head is there, you have friction loss is there. So these all things you have to consider. Because the open loop, each and every time is pumping the water from ground floor to the roof. If it is booster pump, means it is scenario is different, because the pipe is coming from the gravity, right? There is a gravity law is there. So that time you no need to consider the static head, because it's coming from up to down, right? So you have to minus this, what you call this static. Only you have to minus static that time, okay? You have to add residual. And the last residual pressure is the example. If you have this water closet, there's a 40 meter PSA is there. So that you have to consider that one, okay? And when it is come for open loop system, because open loop system will do each and every time pumping the water. But closed loop system is not like this. Already pressurized is there. If you have any expansion or contraction, the pressurization will be control the take over that losses, water losses or in the air, in the pressure losses, it will take over that one. That's the reason we are providing pressurized system. Yes. Any more question?
Yeah, if anyone has any question, please free to ask. We are here to explain all your doubts. Yeah, please.
No problem. Okay, so I will repeatedly say we will do another one session for detailed, which may not detailed, shop drawing calculation. Okay. So which I present now is a detailed calculation. Detail is in calculation. So shop drawing calculation different than this one. Not different, method is different, but similar one. but you have to consider we have to do the isometric diagram, and based on that, you have to do the calculation. So that webinar, I will provide one calculation, a live calculation.
Regarding the fitting pressure drops, for example, elbows and Y's, you have mentioned about considering this based on the equivalent length, right?
Exactly.
But there is other ways of calculation just to consider the coefficient, which I have been using. So can you tell me which one is more accurate?
The equivalent is more accurate. There is that one is you will get the value. That value you can directly put this in the this over on the total pressure loss. But when you do the formula wise, calculation wise, is more better than that one, because you have to consider all the scenario, the roughness factor, everything. Because when you do this equivalent length, and you have to go similar like this straight pipe length. So you have to apply the same formula for this one, because you took equal length. So if example you have this bend is there, so bend is coming at 20 feet or 10 feet. So which is 10 feet of length. So length is 10 feet. So you're putting again like that formulas. So it is more accurate than just the coefficient factors.
Okay, thanks. Fair enough.
Yeah, so any other question, or we can go to the question and answer section now? Anyone? Anyone would like to ask any questions?
Thank you, Nagraj, for organizing such a wonderful webinar.
Sure, we have many more to come. Anyway, no issue.
Yeah. It was a wonderful It was a wonderful presentation. I would like to also present some topic in the webinar. I will chat with you separately.
Yes, sure. Okay, fine. So now I will share the screen. You can see the means like there will be a QR code will be appeared in the screen. So please scan this one. So you will be directed to the question and answer section. Please make the request so I can accept very quickly, and you can see the questions. Okay, please scan this one. Those who are watching in the mobile, if you can't scan this one, I already posted the link also in the chat box. So just to access the link, you will be directed to the question section, but you need to request the question section. Just going down, you can see one request. If you request that one quickly, I will get the mail and I can give the permission for the request. So you can see 10 easy question and answer. We didn't make very tough this time. So we want everyone to get the 10 out of 10. We want more winners this time. So it will be more encouraging, and we love that one. So please scan this one. You can reduce me, then I will assess that one. Yeah. We will give 2 minutes time. So all people can send the request. I will quickly accept that one. So you can start the question. So please submit the answer in 1 minute. This is not that much tough, and we didn't add any calculation also. Just a theory question. Okay, so I got many requests. Now I will start accepting one by one. So you can view the questions. Yes, I served the request all. Anyone want to scan the code again? Yeah, so many people are submitting the answer very fast. So seems like we have prepared a easy questions this time. Okay, so time's up. Already it's already 2 minutes. So I would like to I would like to give you a big thanks to Mr. Victor for giving such a detailed webinar today regarding the chilled water pump head calculation, and my heartfelt thanks to all the participants, because you people raise lots of important questions like static head and flow, and there are different topics. Actually these doubts normally come to everyone's minds when it comes to pump head calculation. So thank you all for making this webinar very insightful, because the success of the webinar is depends on how people react. Yes, you people have done it in a very good way, that you have asked many questions. That was too interesting to know that. We are still the learners. Even we have 20-30 years experience. Every day we are learning something new. So it was very surprising to see that many people ask the questions. And yes, we have 6 more webinars in next 60 days. So we are planning to conduct more webinars related to technical, of mechanical and electrical topics in the coming days. So every week there will be one webinar. So we kindly request you to attend all the events. So we need to reach out more people, because it's like we are moving towards delivering something which will make great impact to all the young engineers who wants to learn something related to the MEP. So we are trying for our best. So we really need your support. And finally, I would like to thank Mr. Victor for once again for a detailed section, and a big thanks to all the participants. So we'll see you again with another interesting webinar. Yeah, Mr. Victor, you want to say something?
Yes, thank you so much, everyone attend this webinar. So we will see soon another one, detailed webinar regarding this pump head calculation. And similar like other head calculation, other pump open loop head, open loop pump head calculation, and then the firefighting pump head calculation. We will see that webinar as well. Thanks again. Thanks.
Yeah, thank you all. Thank you all for your precious time, your valuable time. So we'll see you again. Have a nice day. Good night.